let me do that. So, we're given the data in a different format. For example, when there's a ton of repeats. Oh man, you guys look really defeated. What's up? I'm sorry. I'm so sorry. I don't know how much I've done to contribute to that. And if I've done that, I'm sorry. As a math teacher, I'm used to that. But I'll stop. I'm sorry. Everybody's got stuff now. So if I give you data like this. Can anyone give me any idea what that craziness means? Like if I ask somebody a question like, how many goldfish do you have? What were the answers that I got? What were the answers that people said? If I said, how many goldfish do you have?
0.
Where do you see 0?
36.
Some people said 7. Do you see that? What percentage of the people said 7? 70% of the people said 7. Great. Some people said 8, 20% said 8. You guys with me? So I could have written 77s, 28s, 5 9s, and 5 12s in a big ass list. Again, I don't want to see that shit. Why would that doesn't make any sense because there's so many repeats. It makes more sense to write it like this. Is everybody with me? You guys really with me? No? Okay. All right. So if I was going to start writing a list of data and I wrote 7, here's a list of data, correct? 7, 7, 7, and I did that 70 times. Around the 25th 7 or so, maybe some earlier, wouldn't you guys start going, Jeff, dude, what are you doing, man? Would anybody, I don't know, you guys might not speak up, I don't know. If I was in the class, I'd say, wait, what? Wait, what? Why are you writing 7 so many damn times? You guys, would you agree? Here's my data, 7, 7, 7, 7. I'm just writing up here 70 times. Aren't you guys gonna ask, you okay? Do you need a reset? Do you stuck? Some program running over and over? You guys kind of with me? So it'd be smarter, it would be better for somebody, instead of writing 77s, just tell me 70% was 7. Just say that. 70% of the people said 7. Isn't that a better way to do it? 7. What did people say? Some said 7, some said 7, some said, oh my God. 70% said 7. Everybody with me? So what percentage said 12? 5% said 12. What percentage said 10? 0, 11. All right. These are the only answers I got, and they were repeated this frequently. Okay, I like it. You guys all with me? Since I have it in this format, I'd rather figure out a way to get the mean so that I didn't have to go back to a list. So we developed a shortcut. All the math I tried to show you last time, I tried to show you the old way and kind of a new way to do it. And both ways are the same mathematically. They're exactly the same. So to find the mean, I would just multiply across and add down. You guys sort of with me? Okay. So to find the mean here, 7 times 0.7, 4.9, is that cool? And we talked about list 1, list 2, list 3, and so forth, right? Okay, not a big deal. 8 times 0.2, 9 times 0.5, 12 times 0.05. Okay. Yes?
So x, p of x means mean.
Exact. Well, no. X p of x just means x times p of x. The mean is the sum,
Oh, okay.
which in this case would be whatever the hell that is. 6.95. 7.55. Is that right? Is anybody? Nobody's gonna help me out. They're all like, you get paid to do math, man. Do the math, boy. All right. So somebody can double check me, but I think it's 7.55. It is. It is. Okay. I should have asked this, and that's unfortunate for me, but let me kind of backtrack. How did I know from the beginning the average should be close to 7? From the very beginning, I knew it. Say again? Most of the data points are 7, right? the heaviest weighted dude is 7, and in fact, the next heaviest weighted dude is 8, which is why the average came out to be between those two. And why is it a little bit more than 7.5? Because these guys pulled it up just a little bit. Because they're not very heavy, but they're still going to pull it up a little bit. Does that make sense? Yes, maybe. So again, you don't have to know that going in, but it's a nice way to check. If I got 11 and I see this, I should know I'm wrong. I should know something went wrong mathematically. There's no way I get 11 when that's the heaviest weighted thing. Does that make sense? Okay, maybe. Okay. Again, if you don't understand the whole thing about the weight, you can do all these problems without it. It's just one extra little way of making sure you're on the right track. So that's the formula for the mean. And another name for mean is expected value, and it's just kind of nice that it's sort of like the first 3 letters of the formula is EXP. Expected values. It's just a coincidence, right? Okay, I like it. And I'm the only one. That's okay, Jeff. You're used to it. Okay. So then, to figure out the variance, we did a little bit of algebra. And we figured out a nice formula for the variance was this guy. Relatively nice. I doubt many of us would say that was a nice formula, but it's relatively nice, yes.
So what was the 3 simple again?
Which one?
The 3 simple?
This here?
Oh, okay.
This? Oh, yeah. What's the letter again? Do you guys remember the letter? Sigma. You don't have to remember that, but it makes sense. It's a Greek letter S for sum. Yeah. So whatever comes after that symbol is what I need to find a list of, so then I can add them up. So from this equation, I subtract mean squared from the sum of this, so I need a bunch of these. I'm going to keep doing this, because that's what's going to get you through this, if this makes sense to you. If I give you an equation and it's got this symbol in it, cover it and go, I need a bunch of those, so then I can do what this thing wants me to do, which is to add them up. I can't add them up until I get them, right? And that's why, yes.
So how do you know how many we need?
How many we need?
Yeah, you said we need a bunch of them. So
No, I need them. I just need them. How many of them? This many.
Okay.
I know I got 4 things here, right?
Yeah.
So I'm going to end up with 4 entries.
Okay.
So what column do I need? I need a bunch of those. So I need x squared p of x. Okay. And we talked about it last time. I gave you that handout. The handout's got the instructions. If you want to use the list in your calculator, you can. Right? I always do L1 times L3. I think that's 34.3 maybe? I'm really going to need somebody to help me out. Let's see. 12.8, I believe. Try to do this. I love it, Jeff. Let's see. 3.6, and that'll be 3.9 maybe? I'm going to need somebody to help me at some point here. All right. Can somebody double check those numbers?
The 9 is supposed to be
What is it?
4.05.
For this one?
Yeah.
So let's see. 9 times 0.45 is 3.45?
Yeah, no, 4.05.
4.05. Okay. Thank you. Does everything else look okay? Okay. So again, on that handout, you can put this in, you can put this in. L3 would be L1 times L2. L4 could be L1 times L3. And then you can just sum up the list that you need. You guys all with me? Okay? If not, you can just say, I'm not with you, Jeff. And we can do it up. Let's do that real quick. And not show everybody there. So I'll show you how to do this in your lists. Maybe. Oh, hey, all right. All right, let's see if I can do this real quick. Alright, so if I put into list 1, I put 7912. List 2, I've got 0.7, 0.2, 0.05, 0.05. L3, I can make that L1 times L2, right? L1 is above 1. L2 is above 2. And then L4, one way to get x squared p of x is to do x times x p of x. That'll give you x squared p of x, right? Just a smidge of algebra. So L1 times L3. And there we go. Cool. Okay. And again, that handout, when you're doing your homework, you can just have that sucker sit next to you, right? So to do the variance, I just need to add up list 4 and throw it into the formula, right? So if I want to, let me show everybody at home what's happening. So we put all the data in there. So if I want to sum up list 4, you guys, can somebody remember how to do that? I get out of here and I go where? List, which is right above stat. Math, because I want to do math to a list. Yeah, 5th one, that's sum. I want to sum up a list. Sum up list 4. So then this guy, the sum of these things is that business. I love it. Cool. So it's I desperately want you guys to understand, no matter what formula I throw at you, if you just find a summation symbol, whatever comes after it, that's the column you gotta make. Because it wants you to sum those up, and you can't sum them up until you get them. Okay, maybe. So now if I throw this stuff in here, oh man, I gotta hire a camera person. All right. $58.35 goes here. The mean we found was 7.55. Squared is very often a thing that people very often forget. You forget to square that sucker. Let's see. You guys at home, I'm just going to put it in the calculator. What was it, 3.5? So you got this. What is that again? That by itself? Variance, kick ass. So if I want the standard deviation, I got to take the square root of that sucker. Square root of that, which is the answer button right down there. It takes the last thing you see on the screen. So that'll be 1.161. That's acceptable. Okay. Would you say that's a very big standard deviation? I'd say it's pretty small, right? And it makes sense because 70% of my data is the same number. 70% of my data is 0.55 away from the mean. Do you guys see that? So of course the standard deviation is going to be pretty small because most of the data is really close to the mean. Okay, maybe. And again, whenever I do that kind of thing, it's extra. There's nothing in the work that requires you to do what I just did, but it just doesn't make sense. Does what I just got make sense? Okay. And it used to be pretty easy, where if you get -7 is the length of the side of a shed you're going to build, you're like, okay, I'm wrong. But now we're getting this number, and you're like, okay, I got to get a feel for if that seems right. Maybe. And just to show you, in case I think I showed you this last time, but did I show you the shortcut to make the calculator do all the work? Help me out. Which list? This is a trick question. Which list is the data in? It's a trick question.
One more steps.
No, which list, 1, 2, 3, 4, is the data in?
All of X.
1 and 2. If I just tell you this, it seems like I only talked to 4 people, correct? Don't I need both of these to get the complete picture? So watch this. So I'm going to go off of what you said. 1 var stats, stat, calc, 1 var stats, list 1, list 2. Let's see what we get. Hey, we get some familiar looking stuff. I love it.
How did you do that?
All right, I go to stat, calc, 1 var stats. If you have the old calculator that just says 1 var stats, just put L1, comma L2. You guys with me? When you hit 1 var stats, if it just says 1 var stats on your screen with a blinking cursor at the end, type L1, comma L2. Bam. If you got this, my list is L1, my frequency list is L2. And so then it's able to shabow. And again, for anybody who still needs to hear this, that is not doing work. That is checking work, right? So I still have a few people that will write on some homework or something, do this in the calculator. What? No. You got to do it by hand. You can check the calculator. Now that we're outside of the first test, I'm not going to, if I give you a list of data, you can just put it in and get the standard deviation using 1 var stats, correct? But stuff like this, new stuff, you got to show me the work. Okay. Okay. So that was a not as quick of a review, but still semi-quick review of 40142. So incredibly enough, we're going to do 4.3, and then we're going to do a little bit of chapter 5, and then we're going to call it a day after that. Okay. Is anyone, all right. Are there actually no questions about anything we just did before I move on? You guys good? Okay. Oh man, that blue marker was strong. Okay. All right, guys. The last time I checked, and I don't think this has changed. How many people in here, by the way? Let me finish that thought in a minute. How many left-handed people, if you feel comfortable letting me know? How many left-handers in here? I'm not left-handed, so okay. 2, 3. 3. Hands slowly going up. 3, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 26, 28, 30, 32, 34, 36, 30, 40. So 3 out of 40. 3 out of 40 is 6. No, is it 6%? 3 or 40 is 1.5 out of 20, which is 5, so that'll be 7.5%, I think, right? So, I think roughly, okay. So any group of people that I choose or is just chosen for me can have a different percentage. The last time I checked, the percentage of Americans who are left-handed is around 11%. It's been around 11% for a long time. Is everybody kind of with me? Okay. So the kind of problem we've done so far, so this is us, this is our class. They tell me that the probability of a left-handed person is 11%. So it's probably of a not left-handed person. 89%. You guys with me? I like it. I like it. So let's introduce some kind of shorthand, right? And again, basically all of mathematics is just a bunch of old white dudes sitting around going, can we come up with a symbol for all this shit? Because I don't want to write this out forever. That is the short, drunk history of mathematics. So any student who's taking mathematics, you have to go, what kind of symbol did they use? What the hell does that symbol mean? You're just catching up with all the symbols and what the hell it means. So one quick way to identify this is we would call this little p, and this one we call little q. So little p, dude, is the probability of success. So if I'm looking for left-handed people, A success doesn't have to be a good thing. If I'm on the battlefield and I'm looking for dead people, that's not a good thing, but it's what I'm looking for, so that would be called a success. Are you guys with me? If I'm looking for rabid squirrels, finding a rabid squirrel would be a success. Are you with me? It's not good for the squirrel, it's not good for anybody who comes near it, but it's what I'm looking for, so that would be a success. So in this case, I'm looking for left-handed people. We're going to call that P, and then the opposite of that will be Q. Now, why didn't I just say right-handed? Probably left-handed, right-handed. Some people are ambidextrous. Some people, of course, don't have both hands. Some people don't have a left hand, right? Some people don't have either hand. So I'm not gonna. That's why I'm being very general. Left-handed, not left-handed. That covers everybody. Correct? Okay, I like it. I like it. Okay. So the kind of problems we've done so far. Let's do a problem like what we've seen before, and then I'll show you how the next section just sort of like expands on that. We've seen problems like this. I pick 5 people. Probably the first one is left-handed, and the other 4 aren't, right? So I pick 5 people. Probability first is left-handed, last 4 not. You guys with me? So this one you guys can do. This is a problem we saw before. How would I do that probability? How many empty spots do I have? 5. What goes in the first spot? Yeah, 0.11. Let me put a little p dude there. So what goes in the rest of them? Q. So I'll put 0.11 times 0.89 to the, just to cut to the chase, 4th. Are you guys with me? You guys with me? Okay. And then you would just do that. Somebody help me out. What the hell is that? Let me see, what is it going to be, Jeff? 9, 8, 7, 6, 0, 6. So like 0, 5, 8, 4. I don't know. I'm making shit up. Probably less than that. I don't know. It's around 5%, I think, is my guess. .069? Oh man, it's bigger than I thought. Okay. Let's do that, Joe. Okay. 069. Oh? Yeah. Okay. Okay, so we've seen that kind of problem before. Do you guys remember the whole discussion we had about why at least one, that question sucks? We had this big discussion about it. I don't know if you, hopefully you understand why that would suck. If I said, I pick 5 people and I want to know the probability that exactly 1 is left-handed, why is this work not sufficient? Why is that work not sufficient? If I pick 5 people, like I picked this row, you guys have 5 people in your row. The work we just did was, he's left-handed and the other 4 people aren't. Does that answer this question? I want exactly 1 person to be left-handed. Does it say anything about the first person has to be left-handed? No, it just says I want 1. So look at these 5 people. Everybody stare. No, I'm sorry. This row right here, these 5 people. How many ways is there for exactly 1 of them to be left-handed? Either he's left-handed, or she's left-handed, or she's left-handed, or she's left-handed, or she's left-handed. You guys all with me? So there are 5 ways. You guys with me? So let's list them out. Let me see. Urgh. I miss my rooms that were set up for writing on the board. So exactly 1 lefty would look like P, Q, 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 Q. So that's lefty, 4 not. Or, you can do it, Jeff. Q, B, Q, Q, Q. Which would be not, yes, no, no, no. Okay, I think you guys get the idea maybe, right? Can't I just float? Oh, that's going to sound terrible. Can't I just float the P through there? Q, 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 P, Q, 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 P. Letters get weird when you write them a lot. Okay. Does everybody understand what that list needs? Real quick, you're not going to have to write lists like this. We're going to see very quickly why this exact problem has a very small list of possibilities. Does everybody agree this is a very small list, especially when you consider, did I already talk to you about, has anybody ever heard about the number of pizzas you can make with just like 13 toppings of choice? They're in the millions, yes? So this list will get very freaking huge very quickly. If I had 8 people and I wanted to choose 3 to be left-handed, this could be the first 3, or the last 3, or the first 2 and the last one, or the middle one, the last 2, and the first 3. Holy shit! That list gets stupid big. We're going to develop a way to have something count how long the list is for us. Namely, of course, the stupid expensive calculator, right? Every single one of what I just wrote. By the way, is everybody cool that there's an or between each one? It's either the first person or the second person or the third person, blah, blah, blah. Is everybody cool that there's ands in between here, of course, right? The first situation is he's left-handed and she's not and she's not. You with me? So what does every one of these look like algebraically? Each one of these looks like what algebraically? P times Q times Q, 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 Q times P times Q, 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 Q times Q times P, Q, Q. What do they all look like algebraically? What's Q times Q times Q times Q?
Multiplication.
It is multiplication. What is Q times Q times Q times Q? Q to the 4th, thank God. So P, Q to the 4th. Each one of them looks like that, correct? And why does that make sense? What did P stand for again? A lefty, specifically, in this case, it's a lefty in general success, but in this case, it's lefty success. And didn't the question want one left-handed person and the other 4 not, right? Now, we already did that work there, right? 0.069. But how many of these? What's OR mean? Add. 1, 2, 3, 4, 5. So I got 5 of these. So to answer this question, it would be 5 times 0.11 times 0.89 to the 4th. 1 success, 1 lefty, the rest not lefty. And there are 5 ways to do it. So you get the neat number 0.345. So any group of 5 people from the U.S. that you pick, there's a 34.5% chance that exactly one of them is left-handed. You guys semi with me. Do you see how this kind of idea? Are there any left-handed chairs in this room? I always forget to check. But most of our rooms have left-handed chairs. Are there any left-handed chairs in this room? Oh, well, they suck. Maybe not. But my other classroom, okay. So I forgot to check this room. Normally there's about 4 or 5 left-handed chairs in a room. And do you see how this kind of knowledge would lead to knowing how many chairs to put in a room for a left-handed person? Does that make sense? Now, of course, someday I'll should get the chair that can be either one. That'd be great. I think one room we have has those. Anyway. Okay, so there are immediate real-world applications of what we're doing. Okay, so just to give you an example of how difficult this number will be. By the way, why was that number 5? Remind me. Why was there a 5 here? Because there's 5 ways to do what it wants me to, correct? All right, so watch this. This is where the math teacher goes and makes everything really hard. Okay. And then he shows you a shortcut afterwards. So let's say I have 80 people. Right? I choose 80 people. And I want exactly, you can do it, Jeff. Let's say 12 to be lefties. Can you start to imagine what it would be like to try to get the complete list created? Can you imagine that? So it could be the first 12. and then the last 68 are not. Or it could be the first 11, and then you float the P through until it. Do you guys start to understand how absolutely insane producing that would be, right? So of course I'm going to make you, no, I'm joking. We're not going to do that. But I want you to understand, every single one of these things, can you guys tell me what every single one of these things would look like? P to the Q to the what? You could do it. Every single list has to have how many P's in it? 12, because I want 12 successes, correct? So how many failures do they have to have? 68. So then we know this much already. 0.11 to the 12th, 0.89 to the 68th. All we're missing is how long the list would be. Do you guys see that? If I just had a freaking machine whose job it was to count shit, that would be amazing. Oh yeah, okay.
Yeah, Joe, who's smart?
All right. So I want to show you how to put into your calculator. Hey, calculator, can you please tell me how long this list would be so I don't have to make it, right? So let's see where that command is. And the funny thing is, let me ask you, does it make sense to think, if I have 80 people, isn't this question saying, I want to choose 12 to be left-handed? And I'm trying to write every which way I could choose 12 to be left-handed. Are you with me? So that's beautiful because the letter C plays a huge role for you guys. The letter C plays a huge role in what it looks like in the calculator. So, by the way, let's do this real quick. I should have done this first. Anybody need to borrow a calculator? We're going to do a few things on the calculator, so you might as well get one. Please tell me if the battery needs some charging. I got you. Please come right back to me if your battery is low. Okay.
Is there enough battery on it? It's like one like little.
Yeah, I'll get you through.
Okay.
Okay. If it starts to glow red, just tell me. All right. What were you about to do? Oh, that's right. Okay. So there's a really cool little part of this calculator. There's a couple of things about counting that I don't really focus on too much. There's something called combinations and permutations, exactly. And that's one little thing I don't really do a lot with. I just focus on the combinations part. And I don't even call them combinations. I call it choose because it makes sense. 80 people choose 12 to be left-handed. That's exactly what it's going to look like in the calculator. So everybody who wants to play along, let's see how long that list would be. Wait a minute, what am I doing? Rise. Everybody needs new batteries. Okay. So if we put in there, let's hit clear, get a nice fresh screen. Now everybody put in there 80. Now we're going to go somewhere we don't go very often. Go to math. Go to probability. And then the third one, so don't use National Public Radio. Go to NCR. Right, a little Fallout reference there, but NCR is just, N is like the number of things, and they use the letter R. We're going to use the letter X for the number of successes. So 80, number 3, 80 choose, what was it, Jeff? 12? 12. Not 13, buddy. You can do it, buddy. There we go. So it should look like that. If you have an older calculator, it might say 80, NCR, and then just put in there 12. Okay. Let's see if we all get the same number. Does anyone know what that actually is? What does that little E dude mean, remember? Well, no, sort of. Yeah, how many movements does times 10 to the? So you have to move the decimal 13 times. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 4 zeros. That's the number we're talking about. That's how long this list would be if we actually created it. You guys all with me? Does everybody really understand that that's all I need help from the calculator is to find how long that list would be, because I already know each of them is going to look like this. Why? 12 successes, the rest must be failures. So what do these two exponents always have to add up to be? These two exponents. N, the total number that I have, correct? I love it. Just another little check. So, now we can do this. You all agree it's a very big ass number, correct? That's bigger than numbers I normally use. Yes? Well, me, I don't know. Yeah, even me. The other piece of this, do you guys understand 0.11 to the 12th is going to be stupid tiny? And 0.89 to the 68th is going to be even stupider tiny. Yes? Do you like it? So it all kind of averages out. So if I do it all at once, here's what you're going to be doing a lot of. 80. We're going to do it all at once. Math, probability, number 3, 12. Now watch this. Do you see how I'm down at the bottom here? So if you have the older calculator, it's actually kind of nice because you have to do less of what I'm about to do. So you have to hit the over arrow to get back up. You with me? 80 choose 12 times 0.11 to the 12th. So I want 12 successes times 0.89 to the 68th. Let's see if our calculator can handle this. Did I just make this problem up? I did. So again, 12 successes, the rest failures, and there's this many ways to do it. Sweet. All right. The first part of that is crazy big, and the last part of that is stupid small. So when you multiply together, it kind of averages out. Did everybody manage to get that number? If not, let me know. Yes. Okay. So 80. Math. Probability. Number 3. 80. Choose 12. Hit the over arrow, or else everything you type is going to be down there, and it won't be 12 anymore. So you hit the over arrow to come back up to normal. Times 0.11 to the 12th. And then notice that the over arrow again to come back down, right? Times 0.89 to the 68th. So you got, Jeff, you can do it, buddy. You gotta be careful if you're in the subscript, you gotta come back up before you continue. If you're in the superscript, you gotta hit the over arrow to come back down to keep going. You guys with me? And then hit enter. Thankfully, you get the same answer. That would have freaked me out if I got a different answer. So on your paper, you would write 0.0684 or 6.84% chance of that happening. Kick ass. Okay. So, real quick. Let's say there is a 42% chance someone likes sauerkraut. How do you spell sauerkraut? Something like that? Okay. Sauerkraut, this looks about roughly right. And I want to know if I have 62 people, what's the probability that exactly you could do it, Jeff? Let's say 26 like sauerkraut. So let's identify a few things, and let's show the people at home what we're doing. People at home. Okay. Can somebody identify what N is? $62 people. That's the total number I'm working with. N always means the same thing. Thank the gods, right? 62. What's little p do? .42. I love it. So one mistake that some people made was they were putting the percentage number into the equations. That doesn't make any sense. Percentage number is not even a number. It's something we made up as humans to make small numbers make more sense to us. So when I'm doing math to something, you gotta make sure it's the actual number, the decimal. So P is 0.42, so what's Q? 0.58, the rest, always. They're complementary. And let me introduce a new variable. X is the number of successes, and that would be, in this case, 26. Why does it make sense that X, we would use X for that? Because a different problem would just change that number, correct? So that's the number that can change. Everything else is pretty much set in stone for this problem. So we put the variable on that number. So we're going to do the number of things, choose this many successes. Actually, let me do that afterwards. Let's just do it. So how many people do I have? 62. How many do I want to choose to do something?
26.
26, and of course I had to do a palindromic thing, but I want to do it on purpose. And here's where it's a little repetitive, which is nice. 62, I want to choose 26 successes. So how many successes do I want? 26. And what's the probability somebody's a success? 42% chance. So I got 62 people. Choose 26 to be successes. So I got 26 successes. How many failures then? We got 62 total. 26 succeed. How many fail?
36.
36. 36. I like it. You just do 62 minus 26. Those two have to equal the total number. Of course they do, because we're breaking them down into groups. Take a minute, try to throw that in the old calculator. Put it over here also. Let's see. What's your right there? Why am I putting so many parentheses in here? I don't need them. All right. So you can do a quick check and make sure the exponents add up to be the total. And they do. You can make sure the P and Q add. Well, the P and Q always have to add to be 1 because they're perfectly complementary. And so I get this. I get a roughly 10.22% chance. Let me go. Is everybody with that? Do you notice the questions have been very, very specific? Exactly 1 or exactly 26 or exactly whatever, correct? What if I said the probability that more than 50 like sauerkraut? What would that mean? What's more than 50, for example? 51 is more than 50. So I have to do a formula for 51. Or 52. So I have to add that, do a formula for 52. 53. Oh, shit. That's a lot. Okay. So in the homework, you will see a couple, but they're not going to have nearly that many. So I really want this to make sense. If I said part B, or part 2 was the probability that I get less than 2 that like sauerkraut. What's less than 2?
2 people and 1 or none.
1 or none. So you'd have to do the formula twice. Do you guys see that? Do the formula for 1 and add it to what you get for the formula for none. Do you guys see that? Because how can you have less than 2? You can have 1 or none. Or means add. Yes.
So if you were to say the probability that more than, say, 30, we would have to do it 32 times.
Roughly, yes.
to get it to
Yes.
62.
But thankfully, I don't do that kind of thing.
That's what you would do. It would be up to
Yeah.
62 would be what
Yeah. In the book, you'll have to do, I think at the most you have to do is like 5 calculations, which is nothing. Okay. Okay, so, not surprisingly, I have a little handout that I want you guys to work on. I did shoot. So I can do that. I'm going to give this to you and then don't start yet. One more idea I got to go over. All right, so here's the idea. If I took, for this last problem, for example, if I took a bunch of groups of 62, not just one, but a bunch, what should the average number who likes sauerkraut be? How could you figure that out? Let's do an easier example, real quick. Let's say. Does anyone know Shaquille O'Neal, for example? Okay. So he's a basketball player. You don't have to know it. He was a Laker for part of his life, and then he was a Celtic, which really got me confused because I'm a Celtics fan. But Shaquille, I like to pick on him because he was well known for not being able to make free throws. He got better a little bit. So let's say that there's somebody. We won't say it's Shaq. We'll just leave Shaq alone. Somebody makes 30% of their free throws. Right? They make 30% of the free throws they take. And they take 20 free throws. How many free throws would you expect them to make? What percentage do they make? 30%. And in this case, they're taking 20. So what would you expect them? What percentage of the 20 would you expect them to make? 30%. So 30%. You would do 30% of 20, which is 0.3 times 20. You get 6. If they make 7, does that mean anything? Does that the universe quake? Something? No. It's an expected value. It's how much I expect to see, right? He could sometimes make 10, and everybody's like, holy shit, you got it, and then the next few he makes 1. So it kind of averages back out, right? That's why this is the idea of an average. If he took 20 free throws over and over and over and over and over again, overall he would make on average 6 for every 20 he took. You guys follow? Okay. What was the expected value, the other name for? Average. We just figured out a formula for the average. What's the letter for this? N, right? And what's the letter for 30%? What's the letter for the variable? P? I think I heard it. Yeah, I like it. So, do you guys see what just happened? That is the best freaking formula we've had yet for the mean. By far. Every other formula for the mean doesn't involve a summation symbol, and you have to add up a bunch of shit and do stuff. This one, you just take 2 numbers and multiply them, you're done. You with me? So for this last problem, what would the average number of people out of 62 be that would like sauerkraut? What would it be? 62 times 0.42, which in my head I got a little more than 24, which is why I chose this. I wanted to choose something close to the mean because the closer I am to the mean, the larger the answer is. So I had less of a chance to get something like 1e negative 7 or something crazy, right? But what is that really? What is that?
26.04.
Sweet, look at that. All right, so the probability we got from this is just about the highest the probability can be. Does that make sense? The mean should be very close to the peak. It might not be equal to it because that's the median, but it should be really close. So the highest probability should be really close to the mean. So if I put a 24 in there, I would expect a smaller answer because that's further away from the mean. You guys follow? Okay, maybe. Okay, good. All right. Does that help you do any work? No, but it's just a good thing to know. So look at this handout. Where'd it go? There it is. So if you would, please, and feel free to work with other people near you. I'm not going to force you. Can you guys do this for me? Notice one thing. Do you guys see right below NPQ where I have the formula is this, right? I meant to put that up here. Let's see if we can kind of create that formula right now. What was 62? 62 was n. 26 was x. 26 is x. That's q. Now, how did we get 36? Good. So you took the total number minus the successes, correct? Right? The rest, basically. The rest is easy when you're not looking at a formula, but look, the formula has to capture the whole idea, so the formula makes it look worse than it is. All that means is the rest. 62 minus 26 would go here. You guys follow? And what I put after that is just an example to remind you how to put it in the calculator. That example has nothing to do with any of the questions. It's just an example about how to put it in the calculator. Are you guys with me? All right, so go ahead and try to do this. Definitely feel free to work with people near you if you want to. It's concerning.
That's what you should have thought. And then you just want me to put it into decimal. So you did put it into decimal.
All right. All right, guys, let me catch up to you. So one thing you've got to be able to do is identify when you have this kind of problem. These are called binomial probabilities. Why does that make sense? What does bi mean? Two, right? Bicycle, bisexual, bi whatever. So two. Nomial is kind of like, I don't know if you guys remember polynomial. Binomial, monomial. You guys remember that from algebra? So binomial was a two-term thing. So binomial just basically means there's two possible pieces, right? So I have a situation where I have people that either they do this or they don't. Binomial. Do you like it? Maybe. So we call these binomial probability problems. So could rolling a die be a binomial probability problem? Generally no, because how many outcomes are there? But what if I said, I want to know the probability to get exactly 4 5s. Now it's either I get a 5 or I don't. That's binomial. So I could make just about any situation binomial if I just say the probability of this versus not that. You guys all with me? So we call it binomial because two possible outcomes. N always means the same thing for the whole semester, thank to God. So it just means the total number of things we're looking at. What's P in this case? 0.152, I love it. 0.152. And then how do you always find Q? Just 1 minus this. So 848, is that cool? Kind of gave away the game down here, but all right. Again, this had nothing to do with any problem. It was just to show you how to plug stuff in. So, I don't know if this was helpful or not. I don't know. I put little underlines, little blank spots. The probability that exactly 7 smoke. So you can kind of say it like a situation. I've got 44 people. I'm going to choose 7 to smoke. So it's a little repetitive, which is kind of nice. That must mean I have 7 successes, and each success is denoted by 0.152. So how many failures do we have? 37, 11, which is 44 minus 7. So a quick check you can make on every problem you do is, do these 2 exponents add up to be the total? If they don't, you're not going to get the right answer, right? What do you guys get when you do all that? Okay, that sounds familiar. And then you can make that 16.11% if you want to. I don't care. Whatever you do after you put that down, it's up to you. I like it. All right. So, I mean, what if I put a 6 there? What would change? If I had said probably x equals 6, what would change? Everywhere I see a 7, there would be a 6. That's crazy. And then here, there would be a 38. Okay, right? So the format doesn't change because that's the format for every question. I like it. So for x equals 0, I've got 44 people. I want to choose none of them to smoke. So then I get no successes and I get all failures, which in this case, a failure is a good thing, but we'll be okay. No judgment, by the way. I'm just very happy I never started smoking because, my God, one of the hardest things to stop doing. By the way, choose means the number of ways you could choose something. So if I had 5 people, how many ways could I choose one of them? 5 different ways. You guys agree with me? If I have 5 people, I don't care how many people, how many ways is there for me to choose none of them? One way. I don't want any of them. I mean, that's it. There's only one way to not choose any of them is I don't choose any of them. You guys understand? And what is anything to the 0 power? 1. So I got 1 times 1 times this. So to be honest, you could just do this. But again, if you put the whole damn thing in your calculator, you should get the same thing I'm about to get. Let's see, 0.848 to the 44th. Did you guys get that? Okay. And again, it doesn't matter if you put everything in there. It's all 1, so the calculator is just going to spit out the right answer anyway. And we learned that that means go back 4 places, so 0.0007. I'll lock it. 0007, even more undercover. And then the probability of at least 1, in this case, will be 1 minus none. So the opposite probabilities is always 1 minus. We just did the work for none. So then you get that. And somebody was asking me, and I really appreciate this, they were saying, okay, that seems wrong. That seems way too high. But does everyone agree that it's a relatively low percentage that one person smokes? But if I take 44 people, I feel pretty confident. Even with that low probability, I feel pretty confident at least one of them is going to smoke. Do you guys agree? Okay, maybe. And let's really see why even more directly. What did you guys get for the mean? Do it again, 6.688. So I'd actually expect about almost 7 people out of any group of 44 to smoke. So the probability that at least one smokes should be really damn high. Now here's something I did not introduce, and the explanation of this is not as easy as the explanation of this. Most of us don't know enough mathematics to do the full derivation of this. So let's just appreciate the fact that it is a frickin' easy little formula compared to any standard deviation formula we've ever done. This is the easiest one we've seen. So it's just the square root of n times p times q. right? You can just throw that. I'm going to show you what I do normally. I do the mean, and then I do the square root of that times 0.848. Is that what you got for the 2.381?
Can we have those equations on our formula sheet?
Formula sheet. I love it.
Yes, we can.
Totally. Yeah. Now, of course, normally what I do is for a quiz, I'll put the formulas on the quiz. For a test, we'll actually create the formula sheet together. But you can already start to see those are totally going to be on there. This is going to be on there, right? Okay. Now let's see if this sounds at all familiar. I don't think I've actually, have we identified what unusual is before today?
Yeah.
Did I? Okay. And I think, remember it was, you had to go 2 steps up and down, and that's where unusual should start, because for a normal distribution, that's 95% of the data, and there's only a 5% chance you're outside of there. It makes sense to call that unusual, right? So we're going to do exactly that. Would it be unusual to find 15 out of 44? You can't do any probability work to answer that question. You have to set up where does unusual start. So what's the mean? It was, all right, now add 2 of these. Add 2 standard deviations. 4.762, so that'll be 11.45. Yes, okay, thank you. And then subtract 2 steps. You already forgot, Jeff. I did. I already forgot what that was. Too bad for you. 4.762, so that'll be,
1.92.
thank you, please save me. What is it?
1.925.
1.925? So this is usual. I don't know why I put it so, it doesn't matter, Jeff, it's okay. Would 15 be unusual?
Yes.
Totally, it's way the hell out there. So I could even be more specific. You don't have to be. You could just say it's unusual. I could be more specific and say that would be unusually high. An unusually high amount of people that smoke. So very quickly, if I say the name Aaron Brockovich, does that evoke any connection for anybody? Somebody did respond. Like, anybody else know Aaron Brockovich? Sure, it's a movie and it's about a real story. She's a lawyer that did some analysis of. She was taking stories from people and made a class action lawsuit against PG&E. They were polluting the water source, and you watch the movie and it's really kind of heartbreaking when you see kids playing in the water and you're realizing they're playing in this polluted water. But this is what people went through. They were losing hair, they were getting all this stuff. So, I know the usual occurrence of cancer for any group of people. That's just a known fact. If I do a study on a certain area and I'm curious and I see that there's an unusually high occurrence of cancer, then I could go in there and start studying the food, I could start studying the water, the air. You guys see what I'm saying? You guys kind of with me? So this kind of analysis can very quickly say you want a follow-up study. If I see an unusually high number of cancer cases, does that automatically mean that there's pollution or there's something happening? Could that just happen by random chance? Shit, yeah. Is the chances of getting 15 out of 44, do you think that's equal to 0? Do you think there's a 0% chance of that? We could calculate it, couldn't we? And we will not get 0. Are you guys with me? There's a higher than 0% chance to get 15. It's unusual. So if it happened, that could indicate something is weird. Just like with Aaron Brockovich and the cancer and the PG&E polluting water. You guys with me? But that could just happen randomly. Are y'all with me? There was a, what was it? There was a study done, this is more of a correlation thing. There's a study done where they realized that around cell phone towers, there were more babies being born than areas that did not have a cell phone tower. Are you guys with me? This is a true study somebody published, but they did it to be a bit of a troll to see what news people would pick up on this and run with it, and a few news stations did. What's wrong with the reasoning that cell phone towers are somehow impacting fertility? What's wrong with making that conclusion? What's true if you have cell phone towers? What's most likely true? You have people, more people. If you have more people, there's a higher chance that those people are going to make more people, correct? So if there's no cell phone tower, you probably have less people. You with me? So of course there's going to be less babies being made around where there's no cell phone tower. You guys kind of, I don't know why I went up in there, but so you have a certain expected number of babies for a given number of people. That would be the correct way to do that analysis, because that would take into account how many people there are. Okay. Enough of all that. Any questions from this? These are exactly the kind of questions I like to ask. Let's do a speed round real quick. What does he mean? What does he mean by speed round? What does that mean to me? We'll find out. What time I got? Oh, I got time. Let's say that there's a 73.2% chance of something, and I pick 38 people, and I know the probability that X is 4. Can you guys set up the formula for that? This is me just being tapped in terms of creativity. Chance of something. I don't know. So what's N? 38. What's P? 732. And what's Q? 268. I love it. To set up the formula, again, so many formulas you can read like a sentence. I've got 38 people. I'm going to choose how many? 4. So how many successes do we get? 38 people, I'm going to choose 4 of them to be successes. So I have 4 successes and I have how many failures? 34. I love it. You guys see how that flows? Maybe. So again, the formula, we created the formula. Did you guys notice? We created the formula after we did a couple of problems. Do you remember that? The formula makes it look worse than it is. The little n minus x dude, there's no mathematical way to put in the formula the rest. Can't just write the rest. That doesn't make sense mathematically. Mathematically, it's got to be n minus x. When students see that, you think, what the shit is that? It just means the rest. That's all it means, right? Why did you guys put 34 here? Because 38 minus 4 is 34. So mathematically, it's n minus x. What goes there? Okay, I love it. I love it. So these kind of problems flow. How do you pick this kind of problem out? If, for example, you're looking at a final exam and it's got every damn problem we ever did in this whole class, and you know, like, which one is a binomial probability problem? It's going to be one where they give you a % likelihood of something. They have a certain number that they pick, certain number of people or whatever, and then they ask you what's probably that 4 of them will do this thing. There's a very specific look. That's why I like to call these NPQ problems more than binomial problems, because if you can see an N and a P and you can create a Q, okay, that's what kind of problem you're looking at. It's a binomial situation, right? Okay, maybe. Can anyone tell me if this is going to be a high or a low probability?
Very, very low.
Very low, even before you put it in, because the highest power is on the smallest probability. So this is probably stupid small. 16 zeros, okay. All right, good. I like it. Okay. All right, so any other questions on this kind of thing? Okay, last thing for today. I'll stay up here since I got it all set up. Any of you guys, anybody play darts? Anybody throw darts ever? Not professionally. Have you ever played with darts and a dartboard? Anybody? Okay. All of you understand what it looks like, correct? Okay.
So there's a lot of different kind of games you could play. And I'm going to draw just a piece of this because otherwise we're going to just sit here and watch Jeff pathetically trying to draw. Okay. Blah, blah. So the triangles go all the way around, correct? So if you're just a little kid and you got a dartboard somewhere, you got the ones like the magnetic things so you don't accidentally stick in your little brother's head. That may or may not have happened in real life. Sorry. You go to bars and all kinds of things can happen. What would be a way to impress a friend of yours? Of course.
Go straight to the middle.
Yeah, hit the bullseye. Why is that impressive? Exactly. Now you're like, I know what this guy wants to hear. No, you're good. No. I'm not saying that like a bad thing. I love it. But the probability of getting it into that little circle would be low. Why is it lower than the probability of getting it into this triangle, for example?
A lot bigger.
Say again?
It's a lot bigger.
It's bigger. The area of that is bigger, correct? So watch this. This is really pretty cool. Let me see if you guys go with me. If I call the probability of getting it on the dartboard 1, and I know the area of this, let's say, for example, let's say the area of that is about 10% of the whole area. I don't know, I'm just making something up, right? We could do the math if you wanted to, but let's just pretend like it's 10%. Then what's the probability of getting a dart in there if I only count the ones that hit the dartboard? I don't count the ones that hit around it or hit people walking by. Ouch! Go away. If I only count the ones that hit the dartboard, what's the probability it gets into the bullseye if you're just randomly throwing? You guys can do it. There's 10% chance, correct? If I'm just randomly throwing at the dartboard, why is it so much more impressive to get in there over and over again? Because in general, there's just a 10% chance to get in there. If I make it a bigger bullseye, now it's less impressive. It's like making a golf hole bigger, right? Because it's giant. And you're like, look at me, look at that. You know, who cares? Getting that little dude, right? Or a hoop, a basketball hoop. You make that thing giant. Who cares that you got it in there? I don't care. You guys all with me? So intuitively, you all intuitively have a grasp that the area of something is related to the probability of getting that thing, correct? You all have that sense. You all know this intuitively. If I get it in here, that's not as impressive as getting it in there. And especially if I get it in there over and over and over again. Now you're like, holy shit. If I get it in there once, could it have been a fluke? So I'd have to repeat that same trial over and over again and show you, look at me, I can do this, right? Okay, maybe. Okay. So if I have any probability situation and I can represent it visually, graphically, the answer to any question would be the area related to the question. So what do I mean by that? Let's do one example of a probability that I'm talking about, and then we'll head out. Yeah, we'll get out of here early today. What's called a uniform probability. I always make the mistake, and I'm not going to make it this time. Let's say that it takes Jeff anywhere between 1 and 10 minutes to find his car keys. You with me? So you're all like, just get that thing where you can clap and it does something, I don't know, or whatever. Yeah, there's an app on your phone, you can actually find it. Whatever. You guys all with me? And it's uniformly distributed. That means that there's no more likelihood that it takes you 1 minute, than 10 minutes, than 7 minutes. They all have the exact same chance. How many outcomes are possible, by the way? No, just a little more. Could it take me 8.73962 minutes? Yep. So how many outcomes are possible? Beautiful. No, not 10. Infinite number of possibilities, yes? Because what kind of data is time? Is it discrete or continuous? Well, pretend like it's a continuous. Don't any quantum mechanic people come at me with, time actually is impeccable. No, let's just say it's continuous as far as we can experience. You with me? Okay. So the way this is going to look then, every single one, if I think of drawing a histogram, for example, wouldn't all of the bars have the exact same height? Because I said it's uniformly distributed. No time has a higher chance than any other. So now the question becomes, how tall should this thing be? So if the total area would mean 100%, if I only count the darts that hit the board, what's the probability that it hit the board somewhere? And count it, 100%. So I want the area of this whole thing to be 1. Because according to the write-up, what's the probability I find my keys between 1 and 10 minutes? 100% chance. Is everybody with me? What is the width of this? 9, yes? Y'all with me? So how tall does it have to be so the area is 1? If the height was 2, the area would be 18, exact, right? So the height better be less than freaking 1. So what times 9 is 1? What times 9 is 1? That's what I'm asking, correct? I want the area of this to be 1. I love you guys so much. There's an idea, it starts with the letter R, like reciprocal. Yes, what does a reciprocal do? What's its job? What's 9 times 1/9? What's 9 times 1/9? Freaking 1, yes? All right, so whatever the width is, the height is going to be 1 over that. Does that make sense now? Does it make sense that I want all the probabilities in any given situation have to add up to be 1? Visually, that means the area of this needs to be 1. So whatever the width is, the height's going to be 1 over that. Now, what if I ask you this question? What's probably that it takes me between 3 and 7 minutes? Here's the beauty of this. I've got a visual of the situation. What is the area related to the question? Here's 3. Here's 7. What's the area of this? Well, how wide is it? 4. And how tall is it? 1/9. So there's a 4 out of 9 chance. 0.4444. So uniform distributions are beautiful because all of the little subsections are rectangles. And just like with darts, just like with the dartboard, the area of the question, what's the probability to get the bullseye? All right, the area of the question is equal to the answer for the probability. So if I have a visual of the situation, the area of the question is equal to the answer for the probability. It's the likelihood of that happening. So there's a 44% chance. So obviously we'll do some more with that, but let those be nice. Those are just rectangles. It's almost too nice to believe. So we'll do more of that next time. That's getting into chapter 5, by the way. Okay, that's plenty.